Hello, calculus fans. Today we continue our topic about infinite series. So if you remember so far what we've done, in 11.1 we talked about infinite sequences. And then in 11.2 we talked about the geometric series. We talked about telescoping series. And we talked about, what else? We had the divergence test. And now we are ready to talk about another test called the integral test. And these series tests, are just tests to tell whether or not a series converges or diverges. Generally speaking, it's not easy to find the exact sum of a series. We were able to do this for the geometric series, and also telescoping series, because in each of these cases we were able to find a formula for the nth partial sum, S sub n. We then use this to find the limiting value of a sequence of partial sums. And it is normally not easy to discover such a formula. Because of this, in sections 11.3 to 11.6, we developed several tests that will enable us to determine whether a series is convergent or divergent. Without explicitly finding its sum. So typically, we'll just be able to determine whether or not a series converges or diverges, but we won't be able to find its sum. Since a series involves finding a sum, integrals may be used to assist in determining the convergence or divergence of a series, as well as helping us to estimate the sum of a convergent series. There's a little note here, we're not going to cover the remainder estimate for the integral test. We're just going to use the integral test to determine whether a series converges or diverges. All right, let's take a look at this picture I sketched in here. And you can see what's happening. We've got this f of x. F of x is this continuous function. You can see the curve of f of x here. But it's a function such that f of n equals a sub n. So as I have these integer inputs, they ride along the function. So f of 2, for instance, equals a sub 2. So f of 2 is a sub 2. So at these integer inputs, these discrete inputs, the function's value exists right on the function, so that these inputs, the outputs to these inputs here, these integer inputs, follow the curve. So because of that way it's set up, you can see that if we look at these areas of these rectangles, and each of the rectangles has a base of 1, and so for instance this first rectangle has a height of a sub 1, you can see it right here. So the area of this base times height, 1 times a sub 1, the area is just a sub 1. The area of the second rectangle is just going to be a sub 2, because it's going to be 1, base times the height, which is a sub 2, and so forth on down here. So this one here would be the area. This is a sub 3, a sub 4, a sub 5, and a sub 6. And then they mentioned something here. If the improper integral of this function converges, so in other words, you could interpret this as the area under this curve from 1 to infinity. If it converges, that means that the sum has a number. There is an area under this curve. It doesn't go to infinity, right? It converges to a number. So if it converges, it means that that limit exists, and it's a number L, a real number. And the integral test just basically says that if this area under this curve converges, well then all of these sums of these rectangular areas must converge also, because they're less than that. So if the area under this curve adds up to a number, a finite number, then the areas of these rectangles also must add up to a finite number, because they're less, right? The sum of these rectangle areas is going to be less than the area under the curve of this function here, and you can see it just by looking at the picture. So the takeaway is this: if the improper integral converges, then this this series converges also. So we just have to look at this and see if the improper integral converges, then the series converges also. So what that means is if we evaluate this integral and we get a number, then that means that this thing also converges. It doesn't mean that they converge. Like I can't say, well, this converged to, let's say, 17, so that means this also converges to 17. It does not say that. It just says that if this converges to a number, this also converges. But the numbers probably are not going to be the same number. But we can also get something else from this integral test, because we could draw this a little bit differently. So I used the height of this first rectangle, a sub 1 here, but I also could have used a sub 1 for the second rectangle right here. So let's redraw this figure and then see what other conclusions we can come to. So looking at this one, if we set it up this way, so you see it's really the same thing. We've still got this function f of x. We've got these integer inputs that ride along the function. But for a sub 1, instead of cutting it this way, I went over this way. And if I go in this direction, so I have this first rectangle, area is equal to a sub 1. Again, this is the height a sub 1, and this is the base of 1. So base times height is a sub 1. Over here is a sub 2, a sub 3, and so forth. But now you can see that the rectangles are actually bigger, right? If I add up the area of these rectangles from 1 to infinity, it's going to be more than the area underneath the curve. Also remember from calculus 1, we had the left-hand sum. When we used Riemann sums, we found that it was equal to the right-hand sum as n approaches infinity. So if you use a finite number of rectangles, these are not typically the same, but when a limit is employed so that as n approaches infinity, then these end up being the same. So it's sort of like what we've got here. This is like that same sort of idea. But now if you look at this picture, you can see something else. We can also see that if this integral from 1 to infinity of f of x, if it diverges, so if the area underneath this curve is infinite, let's say if this area underneath the curve is infinite, then definitely this area of all these rectangles added up will also be infinite. So if this diverges, this diverges. So we're basically seeing that these diverge or converge together. They're going to do the same thing. They're sort of locked in. And it's because these inputs to this series, when you have these inputs, the outputs ride along the function. So they go together. So this is the basic idea of the integral test. The integral test typically takes a little bit of work because, as you can see, we've got an integral from 1 to infinity of some function. So we're going to have to use some limits to evaluate these integrals. And integrals oftentimes are not all that fast. So it turns out the integral test is one you typically want to avoid if you can, and try some other tests. A lot of times you can use multiple series tests to test the series. And then usually if you have to, you use the integral test, but it typically will take a little longer than most of them. So let's take a look at this integral test. And here it is. It says, suppose f of x is a positive, continuous, and decreasing function on this interval from c to infinity, and that f of n equals a sub n, so that just means our series is going to ride along the top, right, of this curve, where all of these integer inputs will have outputs that are on the curve. We do have to check these things. We are going to have to check to make sure it's positive, continuous, and decreasing. Otherwise, we won't be able to use the test. But then it works like this. If this integral converges, then the related series also converges. And if this integral diverges, then related series also diverges. So a few important points here. C can be any positive integer. This number c, any positive number at all will work. And it's not necessarily that the function is always decreasing. What matters is that it eventually decreases, for every x larger than some number n. So what that means is it can increase at first, but eventually it has to reach a point where the function starts to decrease and then it continuously decreases. And also, this is an important point that I had mentioned earlier. We just have to know this. Okay, the sum of the series is generally not equal to the value of the integral. So we're going to get an answer for our integral if it converges. But that doesn't mean that's the sum of the series. It's generally not that. And then another note here that's important is this: a finite number of terms does not affect the convergence or divergence of a series. So there'll be times when maybe, as an example, maybe we'll run through this positive continuous and decreasing for a particular series here, and maybe we can't start at 1. We have to start at 5 instead to make sure all these are satisfied. Well, it doesn't matter, because adding on a handful of terms will never change convergence or divergence, right? If a series converges and I add 3 terms to it, that's not going to make it suddenly diverge. And also, if a series diverges, if it has an infinite area and I just subtract a few terms or add a few terms, it's not going to change that. So a finite number of terms does not affect convergence or divergence of a series. Okay, who is super excited about trying one of these? I know what you're thinking. You saw the integral test. Next thing you want to do is try it out. I know. So let's get started. We've got this series here. It says to test for convergence or divergence. Natural log and n squared. So if we want to use this test, we're going to have to make sure, we have to check this, I'll just say it like this, make a little note here. We want to check PCD. We have to check, make sure the series is positive, continuous, and decreasing. And you're not going to believe this, but it happened to be, when I was a Calc 2 student, I remember we had this test question, and the test question said, use the integral test to check for convergence or divergence. So everybody in the class, including me, we used the integral test, and then everybody got that one marked wrong, and our professor said, you can't use the integral test, it wasn't decreasing, or something like that. I don't remember which one of these it failed, but he told us to use it, but we were supposed to write on the test we can't use it because it had failed one of these. So don't worry, I want you guys to have a better life than I had, so I would never do that. But let's just check. So to use the integral test, we are going to have to verify each of these, so let's take a look and see how to do that. I guess we'll just go right in order here. Positive. Okay, let's check make sure. Well, we're looking at this, and we've got, I can think of this as a couple of functions in the numerator and the denominator. So I'll just think of these as functions. Y equals x squared. Right, I'm thinking of this as a function, y equals x squared. And we know that y equals x squared is definitely positive on this interval that we're interested in, 1 to infinity. So that checks. And then the numerator also, y equals natural log of x, is also positive on 1 to infinity. So we are good to go there. Everything's positive. Did you notice anything strange? I said y equals natural log of x is positive 1 to infinity. Well, what's natural log of 1? So natural log of 1 is 0, right? So it's not really positive at 1. So what that means is we will just start, when we do this, we're not going to start at 1, we're going to start at 2. Okay, so technically this isn't correct. So really what I should put there, I should get rid of this part, and let's put one of these instead. We can use an open parenthesis, right? So it's positive and 1 to infinity. So what that means is, just make a little note here, we're not going to start at 1. We will start at 2. Which is okay, because if we're checking this for convergence or divergence, starting at 1 or starting at 2, if I start at 2, I'm just going to have one less term. But that remember what we talked about, that won't affect convergence or divergence. I can't add one term to a number and turn that number into infinity, right? So we're just going to start at 2 for this part, okay, to make sure everything's positive. So now let's look for, let's go right in order, I guess. See if this is continuous everywhere we need. Well, all right. We can do this in parts again. We can say, okay, y equals, I guess I'll just do the numerator. Y equals natural log of x. The natural log is continuous on this interval. Continuous on 1 to infinity, so that's good. Y equals x squared is continuous on 1 to infinity. And I guess we could say, therefore, y equals natural log of x over x squared is continuous on 1 to infinity. All right. So we're good to go on positive, continuous. Let's look for decreasing. Now, normally this is one that we actually have to show some work. A lot of times with these, you can just say positive. You can write positive, put a little check mark. Continuous, put a little check mark. And we really don't need to write all this stuff here. These are easier to check. Decreasing, however, this one we're going to have to do some work. If we want to show a function is decreasing, if you remember the good old days in Calc 1, to show a function is decreasing, you just had to show that its derivative is negative, right? So what we want to do is look at the function equivalent of this series, which would just be natural log of x over x squared, right? The function equivalent of this series. And we need to find the derivative of that function and see where it's negative, because where the derivative of a function is negative, the function itself is decreasing. So remember what I said about the integral test? If you can find another test to use, you typically want to do that because it takes a little bit of work. We haven't even done the integral test yet. We're just seeing if we can use it. So for decreasing, we need to find the derivative of our function. So our function is natural log of x over x squared. So let's do a little practice here. Think back to Calc 1 when you learned about we're losing things like the product rule and the quotient rule. And we've got the quotient rule here. So take a minute and try it out. So what I'm saying is just press pause on this thrilling lecture. Press pause. Try this one out yourself for practice and then check back. Did you press pause yet? Press pause. Okay, try it out and then check back. Okay, hopefully you tried this on yourself. So I'm just going to use the quotient rule. We have low, if you remember the low d high minus high d low, all of the square of the bottom we go. So low, meaning the denominator. Low d high, d meaning the derivative of the numerator. Derivative of natural log of x is 1 over x. Low d high minus high, which is the numerator. D low, d meaning derivative of low, which derivative of the denominator is 2x. All over the square of the bottom we go. X squared squared is x to the 4th, right? Then we could clean this up a little. We get x minus natural log of x times 2x over x to the 4th. And we could cancel an x out of everything, get 1 minus 2 times the natural log of x over x cubed. Right, I just canceled that x out and I just put the 2 in front. And we want to see where this is negative. So think about what we're doing here. Remember, we are interested in 1 to infinity. 1 to infinity. So I know that this denominator is going to be a positive number, right? Because I'm plugging in 1, 2, 3, 4, things like that. So this is going to be positive. So I really just need to see, where is this negative? Let's see where this thing is negative. So I'm going to take that numerator and set it less than 0. So then we could subtract 1 from each side. And what I'm going to do right now is divide each side by -2. And remember what happens with an inequality. When you divide by negative, we have to reverse this sign, right? So that would give us the natural log of x is greater than 1/2. And if you remember, the natural log of x is really log base e. So to get rid of this natural log here, I'm just going to, sometimes you call it take the anti-log, but basically if this is true, then I could have a base of e here and a base of e here just to get rid of this. So we could write it like this. It's sometimes called take the anti-natural log of each side. And we have e to the natural log of x. Really, e to the natural log of x, that's just x. So this is just saying that x is greater than e to the 1/2 power, which is roughly, it's right around 1.64. So we could just say that x has to be greater than or equal to 2. Right? So that means that the function is decreasing when x is greater than or equal to 2. Okay, so we're just going to start counting at 2 instead of at 1. But the thing to keep in mind here, to show this is a decreasing function, we need to see where this is negative. So to see where it's negative, I have to take the derivative, or actually I have to see where the derivative is negative. So I have to take the derivative. So we took the derivative, we set it less than 0, and we solved this inequality to see what values of x make this true. And then we found out that when x is greater than or equal to 2, this is true. So it's kind of a bit of work, but now we're actually, at this point, now we can finally say, okay, the 3 conditions of the test have been met. Now we can take the integral test, or we can try the integral test. All right, so here we are. We have shown that 3 conditions of the test are satisfied, positive, continuous decreasing, and now we're ready to take the test. Okay, so here is our integral. Notice that we're starting at 2, but it doesn't matter. We could start at 5, it doesn't matter, right? We just need to make sure that, we just need to test this and realize that adding a finite number of points won't change anything. So starting at 2 is just fine. So because we've got this infinite limit, and we know that the fundamental theorem of calculus does not work if these are not numbers, then we have to get around this some way. And the technique that we have all been taught is that we take limits here. So this is equal to the limit as t approaches infinity, 2 to t, natural log of x. And you know what, let me just rewrite this because I can see how we're going to have to do this. I'm just going to rewrite it this. I'm going to write it as natural log of x times 1 over x squared dx. Okay, and you can see these are the same, but we're going to have to use integration by parts here to get through this one. So I'm just going to use integration by parts. So we've got u equals dv equals du equals b equals. Remember our little acronym. And you guys love to say this. I don't want to be light for class, right? So what this does is an acronym that tells us what to put in for u. And it works really well. So basically look through our integral here. We want to put logarithms first, then inverse trig, algebraic functions, trig, and then exponential functions. So this one's an easy one. Logarithms go first, so let's put that there. So we will go natural log of x here, which means that over here we've got 1 over x squared, but I'm going to write it as x to the negative 2 because we're going to have to take the antiderivative. So over here, If u is ln of x, du will be the derivative of that, which would be 1 over x. And then over here, we have dv already, so to get v, we have to go in the other direction. We have to take the antiderivative, right? So this uses the power rule, so it's going to go, so this will go up by 1 to -1, then we divide by -1. So we have x to -1 divided by -1, or really -1 over x, right? So then we have, this is equal to the limit as t approaches infinity, and we have, if you remember, we multiply, we go like crossways here, so we have -1 over x times the natural log of x, which looks like this. We integrate that from t to 2, and then we have minus this integral. And it's already a minus here, so it'll be minus minus, so it would be plus. And then we're going to have 2 to t of basically x to the -2, right? Because we've got 1 over x times -1 over x, but we already know about the negative part. So 1 over x times 1 over x is 1 over x squared. 1 over x squared is the same as x to the -2. All right, so if we keep going here, we will get the limit t approaches infinity, negative natural log of x over x. And now I'm going to put this part in here too. So that will give us, again, same thing. This is going to go up by 1 to -1, and I divide by -1. So it's the same thing here. We're going to get minus 1 over x. So we'll put this on here, minus 1 over x. And then these are both going to go from 2 to t. And we can actually clean this up a little bit here, because this is really just going to be minus natural log of x minus 1 over x from 2 to t. So now let's go ahead and plug in t and then plug in 2 and see what happens. This will give us equals the limit as t approaches infinity of minus natural log of t minus 1 over t minus natural log of 2 minus 1 over 2. Do something with these signs here. So let me put it like this. All right, then we can say this is going to be the limit t approaches infinity minus natural log of t minus 1 over t. And then when that negative distributes through, we'll just get plus natural log of 2 plus 1 over 2. Right, because this negative will go through and make that positive and make that positive. But really what we need to do is focus on this part. Because if you look at this limit, we've got negative natural log of t. Well, as t goes to infinity, this goes to infinity. So this is really negative infinity over infinity. Right, it's the indeterminate form. This part here is negative infinity over infinity. So what we can use is L'Hopital's rule to work on this. So let's go ahead and say this is equal to the limit as t approaches infinity. I'm going to put this little h here so that everybody knows we're using L'Hopital's rule here. And what that means for the L'Hopital's rule, we take the derivative of the numerator, which is basically minus 1 over t. Minus 1 over t. The derivative of the denominator is just 1, so we don't even need it. And then we've still got this part here. This is just a constant, so that's not going to change. So that'll just be plus natural log of 2 plus 1 over 2. And now looking at this, we can take the limit here. As t approaches infinity, this term goes to 0. So the only thing we'll have left is this. So our answer for this integral would be this, natural log of 2 plus 1 over 2. We really don't care about that answer so much, other than the fact that it is a real number, which means that this integral converged. So if this integral converges, that means our series converges by the integral test. So the way we could say this is, we could say something like this. So we can see by looking, because we got a number for our answer, we can see that 2 to infinity of natural log of x over x squared dx converges. Okay, so that means that, so this series then, n equals 2 to infinity, natural log of n over n squared converges. And if that converges, then the one we were interested in from 1 to infinity also converges. By the integral test. Okay, so a lot to mention here. There's a lot of stuff happening in the integral test. First, we had to make sure that we could use the test. Then once we did it, we found out that this integral converges. And if this integral converges, that means that this series converges. Now, this isn't the series we were originally asked about, but this series is one term different. There's just one more term on this series. So if this converges, adding one term won't change it. So this also converges. So the series we were interested in converges by the integral test. And now I need to write something in red, because remember, red means danger. Make a little note here, because this comes up a lot. I've already mentioned it at least twice, but let's just mention this again, just to make sure there's no confusion. The value of the integral, so that value we got right here, the value of the integral, this right here, natural log of 2 plus 1 over 2, the value of the integral is not equal to the sum of the series. All right? The value of the integral is only important in that it is a number. And since it's a number, we know that it converges, but the value of the integral is not equal to the sum of the series. So as I mentioned before, showing that a function is decreasing is the part that takes the most work. The other one, showing that it's positive and it's continuous, usually you can just sort of mention those things. But the decreasing, we have to actually show. We can't just say, yeah, it's decreasing. We have to show it. So I'm going to show you a couple things you can do. And these two are completely different because of the fact that there's just a constant in the numerator here, but there is a variable in the numerator here and the denominator. So this one takes a little bit more work. But if you've got one like this is really nice because it's just a constant in the numerator. Okay, so if we wanted to use a function here, we could say, well, the function that's like this one is just f of x equals 2 over 5x minus 1. So we could go ahead and take the derivative of this and show where it's negative, but it's much easier in this case where the numerator is a constant. We don't have to take the derivative in this case, because here's what we can do. We could say this. We could say a sub n plus 1, and in this case, here's a sub n, right? Here's our a sub n. So a sub n plus 1 would be equal to 2 over, what I'm going to do is, where I see this n, I'm going to put n plus 1. So that would be 5, not n, but n plus 1 minus 1. And then if we just clean this up a little bit, this is 2 over 5n plus 5 minus 1, which is 2 over 5n plus 4. But I'm going to do a comparison between this and 5n minus 1. And this happens to be equal to a sub n. If I compare these two, so remember this is a sub n plus 1, it's the next term. This is a sub n, the previous term. If you look at these denominators, this 5n plus 4 is bigger than 5n minus 1. right? N is going to be numbers from 1 to infinity. This denominator is bigger. That makes this whole thing smaller, right? Because they have the same numerator. Bigger denominator means this fraction is smaller. So I can say this, it's smaller. So if you look at what's happening, a sub n is bigger than the next term. That shows it's decreasing, right? Because this could be, n could be any number. This could be 7. A sub 7 is greater than a sub 8, right? A sub 20 is greater than a sub 21. That shows it's decreasing. So this shows that the series is decreasing, which means the function is decreasing. So we need to show the function is decreasing. Remember, these are sort of locked in. This series rides along this function at all the integer inputs. So this shows the series is decreasing, therefore the function is decreasing, and that's all we would have to show with one like this with a constant in the numerator. So this shows, since a sub n is bigger than the next term, that means that next term is smaller, right? This next term is smaller than the previous term. So the series and also the function are decreasing. Now when you have one like this, it's not quite as easy, because if I put an n plus 1 and an n plus 1 here, the numerator gets bigger and the denominator gets bigger. So it's not as obvious as here where they're locked in. So I can't do it that way. If the numerator and the denominator are both getting bigger, then it's not quite as simple. And that's when we're just going to have to take the derivative and see where the derivative is negative. So we cannot just plug in n plus 1 here, because the denominator will get bigger and so will the numerator. And we don't want to have arguments like, well, this one's getting bigger faster than that one. It just gets really messy, especially if these get worse, get more complicated. So if the numerator and the denominator both have a variable, we need to use derivatives. So this series has a corresponding function that would look like this. F of x equals x over x squared plus 1. And this is one of those where this previous technique won't work. So here we need to show that f prime of x, the derivative is less than 0. Because where the derivative is less than 0, remember that what that means is that the function f of x is decreasing. So we just have to find out where that is. Where is it? At what point will this derivative be negative? So we go ahead and we take the derivative. So here's our function. I'm just going to use the quotient rule to find the derivative. So f prime of x equals denominator times the derivative of the numerator, which is just 1, right? The derivative of the numerator is 1, minus the numerator times the derivative of the denominator. Derivative of the denominator is 2x, all over the square of the denominator. Or if you prefer that weird chant, low d high minus high d low, all over the square of the bottom we go. So this would give us, let's see, x squared plus 1 minus 2x squared all over x plus 1 squared. Or in the numerator we would get negative x squared plus 1 over x plus 1 squared. Okay, so if we're going to look and see where this is negative, first notice that the denominator is always positive. It's always positive. So the only way this whole thing can be negative is if the numerator is negative. So let's just take that numerator and see, well, where is this going to be less than 0? Well, I'm going to add x squared to both sides, and I would get this. 1 is less than x squared, which means that x squared is greater than 1. Well, if x squared is greater than 1, can I just say that x is greater than 1? So what this means is f of x is decreasing when x is greater than 1. right? When x is greater than 1, the derivative is negative. The derivative is negative when x is greater than 1. That means the function is decreasing when x is greater than 1. So this is just the different techniques we need to show that a function is decreasing. Another series that we introduced in this section is the famous p-series. The p-series, this is an important series of positive terms. They're all positive, but it's an important series. We'll see, especially later, we're going to use a p-series a lot when we talk about comparison tests, and these are coming up in the next section. But so we'll see these again. But the p-series is a series like this. It's a sum from, in this case, 1 to infinity of 1 over n to the p. And it turns out that this is convergent for p greater than 1 and divergent for p less than or equal to 1. So if you recall the harmonic series, which we've seen before, from 1 to infinity, 1 over n, which was equal to 1 plus 1/2 plus 1/3 plus ... This is actually a special case. This is a special p-series. We've shown that this series diverges. We show that on the handout. And this is a special case of a p-series when p equals 1. So the harmonic series, which is a famous series, and that happens to be a special case of the p-series when p equals 1, which you can see if p were equal to 1 here, we'd have 1 over n, which is exactly what we've got. So by using just this up here, we can determine whether these series are convergent or divergent, because this one is really easy, right? If you just look at this, p equals 4. So this is a convergent p-series. We know it converges because p equals 4. So that will, this has a limiting value. This adds up to a number. We don't know what it adds up to, but we know it doesn't go to infinity, right? This is a convergent p-series. What about this one? Remember, it doesn't matter that this doesn't start at 1. It could start at any finite number, right? And it won't change the convergence or divergence. What's important here is this is a p-series, so look at what p is. P here is less than 1, right? So in this case, this is a divergent p-series. Because in this case, p equals 0.9999. And we know that the p-series is a divergent series when p is less than or equal to 1. This is less than 1, so it diverges. Okay, what about this one? Take a second, see if you can figure this out. This is a p-series. It's written in expanded form here, so it doesn't have the summation here. But let's see if we can come up with this summation formula for it. So you might even be able to see like 2 times the square root of 2, 3 times the square root of 3. So it looks like it's something like summation from 1 to infinity. Looks like 1 over n times the square root of n, right? If you plug in a 1 here, we get 1 times the square root of 1, which is just 1, and then it goes to 2, and 3, and 4. So in other words, we could write it like this, though. We could write it as n equals 1 to infinity of 1 over n to the 3 halves, right? N to the 3 halves. And once it's written like that, then we can see that this is a convergent p-series. Because in this case, p equals 3 halves. Okay, so calculus fans, that should get you started. You should be ready to go, ready to try the homework problems out. So remember the takeaway, the integral test, it works, but it's a decent amount of work. In fact, we'll probably look at about 10, there's probably about 10 different series tests, and of the 10, the integral test takes the most work. So usually when we learn other tests, you'll find out that it's avoid it if you can, but sometimes you can't. So go ahead, try 11.3. Remember, the only way to learn about series is you have to do the homework. So try the homework out and let me know if you have any questions.